let's have the first speakers step up for Principles 2. So we have Sabrina, Abram, and Surabhi, Simha, who work with Max at Simon Fraser University. And to remind everybody again, this is the Principles 2 session. Also to remind you, today is Blue Poster Day. So if you have a blue poster, please man that so you can explain it. And check out the blue posters later.
Hello? Hi. So one of the central principles in locomotion is that humans and other animals prefer to move in ways that minimize energy use. So today, Surabhi and I would like to talk about how we can experimentally study key features of this energy optimization in walking, and then how we can model these features using reinforcement learning algorithms. So Jessica Sellinger and Jeremy Wong from our lab have recently shown that people can continuously optimize step frequency to minimize energy. So they use robotic knee exoskeletons to command a resistive torque to the knee as a function of people's measured step frequency. And by doing this, they were able to manipulate the natural cost landscape shown by the gray curve to get a new cost landscape shown by the blue curve. And throughout this presentation, we will refer to the relationship between metabolic energetic cost and gait as the cost landscape. And they found that subjects adapted their preferred step frequency to converge on the new energy optimum, and noticed three key features of this adaptation. First, some subjects spontaneously adapted their gait and converged on the new energy optimum, while some non-spontaneous initiators needed to be shown a lower cost gait in order to converge on this energy optimum. And lastly, once optimization was initiated, subjects would rapidly reconverge back to the new energy optimum when perturbed away.
Okay. So given these interesting features, Sabrina and I want to further probe the optimization process. And to do this, we designed and built two new systems that can manipulate the energetic cost landscape. So this is the force control system. And here we manipulate cost landscapes by applying horizontal forces that are applied to the hip belt worn by a user as they walk on a treadmill. And we can measure step frequency in real time, and we use that to command forces depending on the metabolic cost landscape that we want to create. And we keep our forces accurate and reliable using the series elastic actuator that Jerry Pratt was kind enough to build for us a few years ago.
Our next setup we will refer to as the incline control setup. And it's similar to our previous setups in that it commands a metabolic penalty as a function of gait. However, here the metabolic penalty is our walking incline. So we are able to measure any number of gait parameters on our instrumented treadmill and then command the walking incline to shift the energy optimum of our chosen gait parameter.
Okay, so now we have two new systems, and we wanted to test if we can test for energy optimization in these two new systems. So here is a cost landscape that we created using the force control system, and we created a cost landscape similar to that used by Sellinger so that we could compare the behavior between these three systems. So at the bottom, this is the adaptation results from the subject, from the force control system, and from the incline control system. So pre-experience here refers to the immediate adaptation we observe as soon as the controller comes on and people are shifted to this new cost landscape. And then, similar to Sellinger, we used an audio metronome to give people experience with different parts of the cost landscape. So R1, R2, and R3, they show the adaptation from after the release from these metronome holes. And finally, post-experience refers to the final adaptation that people achieve at the end of the experiment. So the star shows the final step frequency that people adapted to, and this is significantly different from the originally preferred step frequency that people started from. So now, given that we have three systems and energy optimization of the three systems, we compared the behavior, and we found three strikingly similar results. So one is that in all three systems, some people spontaneously optimize, while some people need specific experience before they can initiate optimization. But everyone, after they initiate optimization, they converge on the new optimum slowly in about tens of steps. After convergence, all of them can rapidly predict the new minimum and reach it within a couple of steps if they're perturbed to any different step frequencies. But we also found a couple of differences between the systems. So one, in the exoskeleton system, all the people converge to or very close to the optimum. But in these systems, while people made a significant shift towards the new energy optimum, they didn't quite converge on it. Another point is that Salinger also created a cost landscape where the minimum was shifted to a higher step frequency, and she saw people optimize to this. We created a similar cost landscape, but we saw that in such a landscape, people prefer to stay at their originally preferred step frequency. Okay, so those were experimental results, and given these behaviors, we also developed a simple reinforcement learning algorithm to reproduce these behavioral features. So this is a video of that algorithm. Our algorithm is essentially a bandit type reinforcement learner, and it starts with a prediction of the cost landscape that is shown by this blue curve here. So it takes a step, and at every step, it chooses a step frequency that, according to its prediction, minimizes the energetic cost. And when it takes this step, it will measure the actual energetic cost at the step and updates its prediction by a fraction of the measured cost. So you'll see this blue curve change its shape as it measures from this new landscape that is the red curve. And on the left side is the time series of this plot, and you'll see the step frequency chosen at every time step. And when it reaches this red vertical line is when the algorithm is introduced to this new cost landscape, and you will see it converge on the new optimum. There you go. Okay, so this was our algorithm, and you saw that it converged on the new optimum, but it did so spontaneously. And we mentioned that only some of our subjects do this. So we have a couple of hypotheses for why the others don't spontaneously initiate. Our first hypothesis is that we think the nervous system may not be able to detect a significant cost saving. So you see that the original optimum in the original cost landscape has 0 gradient. And in the new cost landscape, there's a small gradient. And this is what our algorithm previously used to converge on the optimum. But say that the nervous system has measurement noise in this metabolic cost that is large enough that it cannot detect this gradient. In that case, maybe the nervous system prefers to stay at its originally preferred because it doesn't know that there is a savings. And our second hypothesis is that the nervous system also has a reference cost that is equal to the cost at its originally preferred step frequency. And we think that the nervous system always first updates this reference cost, and only when it detects a cost that is lower than this reference cost that does it initiate optimization and slowly converge on the new optimum.
However, extending this optimization to higher dimensions is actually a really hard problem to solve in real time. So on the right here, I will build a plot that illustrates exactly how hard this problem is. So along the x-axis, we have dimensionality, and then along the y-axis, we have the number of states as dimensionality increases. So let's consider one dimension that the nervous system might consider, and that is walking speed. If we were to discretize this dimension up into 20 different speeds, it'd be a fairly simple one-dimensional optimization problem to solve where it can calculate the cost for each speed and choose the minimum. Whereas if we were to consider a second dimension, say step length, now it has to compute all possible combinations of speed and step length. And this problem grows exponentially as we consider more and more gait parameters like knee flexion and toe clearance. In fact, the nervous system may represent these dimensions in a completely different way, such as combinations of hundreds of active motor units. You can see that for a realistic number of dimensions, say 100 dimensions, we have an unrealistic amount of states to evaluate that is close to 10 to the exponent 130. So Surabhi has mentioned that we were able to reproduce our experimental results for energy optimization in one dimension using a simple reinforcement learning algorithm. So what I wanted to do was use this model that has a discretized landscape to extend this to higher dimensions. And when we did this, we found that the learning rate, or the steps to converge on the energy optimum, increased exponentially with dimensionality, as well as the memory to store the cost landscape also increased as the number of discretized states per dimension raised to the exponent of the dimension. So does the nervous system have clever tricks to overcome this curse of dimensionality? Maybe it represents the cost landscape as a polynomial where it only has to remember the polynomial coefficients. And when we implement this on our model, we find that instead the learning rate increases linearly with dimensionality, And then also the memory only increases as the number of coefficients raised to the dimensionality. However, this is still a problem for the nervous system, who is limited to the number of steps taken in a day and also the number of synapses in the brain. So how does the nervous system deal with the curse of dimensionality? Towards understanding two-dimensional optimization in walking, we have tested for energy optimization in step width and step frequency independently. And we have found that people will adapt their width wider than initially preferred to converge on the new energy optimal width, as well as adapt their frequency lower than initially preferred towards the new energy optimal frequency. And our next step is to test these two dimensions, or test for energy optimization along these two dimensions simultaneously. Thanks.
Great. Questions? We have a few minutes. What's the question? Yeah, here you go.
So, on one hand, you said this exponential explosion really relates to you have to evaluate all the possible combinations and then do a discrete search. On the other hand, you mentioned that actually the brain may or may not detect some gradients in that, which is kind of a different approach to finding the optimal. How do you think, after all, the brain adapts or finds a better solution? By gradients or by doing discrete searches, trying out things?
Oh, so that was just two hypotheses that I presented, which we want to test experimentally. So we don't know how the brain does that, but we can form hypotheses about how we think it might do it and then test.
It's the right one now, or
well, I mentioned
the more
that
plausible one?
If it were to discretize up the landscape, like, it's a really hard problem to solve for a realistic number of dimensions that the nervous system has to handle. So we think that it does something smarter than that, and one hypothesis is function approximation. Or gradients.
Can we kick it back to you?
You mentioned this idea that you need to estimate the gradient around the point where you start. And so a key point in reinforcement learning is exploration. And I was wondering if you have something to say about how people naturally explore. So do people's natural variability predict whether they will optimize or not?
So actually, we do have a slide from Salinger. So she found that so there were two groups of people, so some who spontaneously initiated, some who did not. And she found that the people who did spontaneously initiate optimization had a higher variability in their step frequency, as you can see that. So you see that red? Yeah. So that's a spontaneous initiation. So we do think there is some relationship, which is exactly what you're saying. So reinforcement learning is based on the explore thing. So people are maybe, for whatever reason, some of them are naturally explorers.
Oh, sorry. Yeah, so here you can see that they have a higher variability compared to the non-spontaneous initiator, which may give them a better sample of what this gradient is and kind of tease out the noise that we have in the metabolic cost.
We're going to take a Slack question next from Doug.
Am I good? There we go. Can differences in the setup, such as the exo, the force, or the incline, teach us anything about what sensory feedback pathways people use to real-time optimize?
So here we're assuming that what the nervous system is optimizing is metabolic cost energy, so that's our setup based on. So we think for this purpose, the nervous system is sensing metabolic cost, and it could be sensing it directly, or it could be using a proxy for that. So that's the basis.
Yeah, and we could build, I think that our specific setups are testing we're measuring metabolic cost, but if we were to build a different setup that can tap into the sensory system to determine what those sensory signals are, then that would be one way to study that particularly.
Yeah, you want to pass it back?
Just along those lines, were there differences in they probably were different subjects, but were there differences in the three kind of testing modes in terms of the number of people that spontaneously initiated versus not? Where something like an incline, people maybe generally associate with raising their energy cost up or down, even if it's step frequency that's really controlling that. So I'm just wondering if between the three, there were differences in that initiation which might lend insight.
differences between the
differences
swans?
in initiation? No, so I think that's one of the similarities that we pointed out, that in all of them, some people spontaneously initiate and some don't. And so one of the reasons we developed this force control system, we developed these new systems, is to test that hypothesis. So in the exoskeleton system, we're limited in the range of metabolic cost changes we can do. So the landscape is, the gradient is, we don't have much control over how much we can change it. But in the force control, for example, we can make it really steep or really shallow. So that's one of the hypotheses we want to test. So we want to make a steep landscape and see if we can get more spontaneous initiators and use it. No, so we've only tested the shallow landscape, and we have not seen nothing, yeah.
We'll take one more question as the next speaker sets up. So can you pass the mic? Yep, thanks.
So I guess this is not something that you did, but I wanted to ask your opinion on this. If you generated a cost landscape that was completely flat, do you think that people would be uniformly distributed along that, or would they converge onto something else based on some other thing that they care about?
Well, we for sure think there's lots of things people care about. It's not just energy that people care about. We are manipulating the energetic cost landscape. So if we make the energetic cost landscape flat, there'll be other objectives that people care about. So it depends on what those look like to determine how people walk.
Okay, but I guess the specific question I'm asking is, say you let them explore the completely flat energetic cost landscape and take them to all the different points, and then you leave them at some point. Do you think that they would just stay there, or would they keep jumping around because it doesn't matter?
I think that based on the exploration maybe that you give them throughout this space, they would determine what the actual global optimum is of the objective function, which is maybe a weighted combination of other terms other than energy, since that is flat, and then not stay there when you release them, but go back to what they have determined throughout exploration.
Okay.
Great. Well, we have to cut it off there. So let's give them another round of applause and have the next speaker come up.